Hello, my name is Osvaldo Gomez, and I am going to talk about mapping MLOps maturity levels into reality. I am a senior IT MLOps engineer from Roche Group, and Roche was founded in 1896. It's present in over 100 countries, more than 90,000 employees, and it's one of the top three biotech companies in the world. It's a leader in the field of personalized medicine. And Roche Global IT Solutions Center was founded in 2004 in Poland, Canada, Malaysia. It has over 700 full-time employees, 5,000 contractors, and out of those, 50 are data scientists. And we are considered the headquarters for software development for Roche Group, and we have over 1,000 portfolio solutions. So why should we care about MLOps? So 98% of IT leaders believe that MLOps will give their company a competitive edge and increase profitability. And at least 50% of ML projects will not be fully deployed into production by 2022. So our purpose is doing now what patients need next. And artificial intelligence is seen as a driver in this purpose, in this goal. And we have a very ambitious goal, which is supporting basically delivering twice as many medical advances to society at half the cost, and adding artificial intelligence algorithms for whole slide image analysis offers the potential to bring important new information to pathologies that can profoundly impact patients. So like I said, AI is seen as a driver, but in order for AI to actually deliver any value, you need MLOps. Before we zoom into MLOps, let's talk about the value chain in a pharmaceutical company. So you start by research and early development, and Roche is actually one of the top companies in the world that invest the most amount of money in research and development. So then it goes into product development, regulation and safety, production and supply chain, registration of commercialization of a medical case, and support functions. So let's talk about the connecting AI and patients, and how are we going to achieve this? So giving you a small example, so the small molecule research, molecular properties are key to effective decision making in small particle research projects in the process of researching new drugs. So you start with graphs and 3D chemistry, and all of that goes into a molecule registry. And then you add support vector machine, naive Bayes, deep neural networks, an ensemble of trees, and you end up with experimental data with over, with hundreds of features. So, this can really help move these initiatives forward faster. And another example is searching for similar patients. So you start from standard biopsy and procedure, and then you end up with a big data science problem, which is you put it in the microscope, you generate some data, and then you do some next generation sequencing, and all this data obtained during the research may be used in the future for data science, for mapping multiple patients into clusters that you can perhaps give them a specific drug that will help cure a specific type of person based on their genetic sequencing. So, really exciting and super passionate to help in this area in any way I can. So this is the mapping, but let's talk about how complex this picture is, because you all know that that this is complex. So let's just zoom in a bit. You have data engineers, data scientists, DevOps, and you have to first prepare for production. You have to do some runtime environment, risk evaluation, QA, okay, and then you develop to production. So development to production, you do elastic scaling, containerization, CI/CD. So you need like data in DevOps for that. You obviously have to invest in monitoring and feedback loop, logging, alerting, input drift, performance drift, online evaluation, and then you have to have an SME to tell you what is, if it's if the monitoring is performed tracking the right set of metrics or not. And obviously you have to develop the models, and you need data scientists, but in order to get to train the model, you need data. So you need data engineers for acquiring the data, preparing it, Then the data scientist does feature engineering, model training, and it's complex. So to navigate this, we used Google MLOps maturity levels. So when you start at level 0, you have nothing. This is like 90% or a very large percentage of all AI projects in production or in development right now. Yeah, it all starts with this. No, you start with like manual experimental steps. You obviously do some data extraction, but data preparation, training, and evaluation and validation happens in Jupyter notebooks and totally isolated in a laptop somewhere. And you train the model, and if the best case scenario, you put it in a model registry, and then you call the ops guy and tell them, hey, here's the model registry. Could you deploy it via an API? And they're done. But this is manual script driven. It's infrequent release of iterations. You cannot release a couple times per month or per even takes a while depending on the type of problem. But this is level 0. And then you want to improve, but you need to know where are you going, what is the direction that you should be taking. So you go to level 1, and this is from delivery of a model to delivering a model producing pipeline. Let me say this again. You go from delivering a model to delivering a model producing pipeline. So now you have rapid experimentation, continuous training of the model, experimental operational symmetry, modularized code for components and pipelines, continuous delivery of model, and pipeline deployment. So note here that it's not like fully automated. You have an orchestrated experiment, then it goes into the source code. The source code is gets pushed to the repository, and the repository then you push it to the pipeline deployment. So from the source repository goes to the pipeline deployment. Then you have this automated pipeline. And for me, the level 1 is all about the automated pipeline. If you have a pipeline that automatically does data extraction, data validation, data preparation, model training, model evaluation, and model validation, you're very close to being in a very good place. There's things here that are great to have, but might take a while, and you might not immediately implement them. Depending on the risk that what you consider the most risk, the highest risk situation. So anyways, you have this automated pipeline, you put it on the model registry, and the trained model goes into production and via a model serving, and you have a prediction service. This prediction service then gets monitored, and this monitoring then can potentially re-trigger the automated pipeline if there's some model drift or anything. And then it goes, it can actually trigger again some data analysis, and it all starts again. But let's now move to the second level, and it's tricky to see the difference. But if you essentially, I put it here in bold letters, so it's full automation via CI/CD/CD. So now you don't rely on human pushes to make this go, from orchestrated experiment all the way to production. You don't have to touch anything. Everything happens automatically. So essentially you are a data scientist. You're working on you have an orchestrated experiment. So you're doing this maybe in your laptop, but it's all orchestrated. And then you're sure that you're happy with what you have. You push it to the repo, and then you have CI, build, test, package, pipeline, and components. The packages go there into the next stage via CD. So continuous delivery could mean pipelines for Kubeflow, and obviously you package the source code if it's in Python. Everything happens here, but you deploy automatically via Argo CD or however you deploy. And then here it moves on to the automated pipeline, which is the same as I described in the last step. And usually this happens within some orchestrated like Kubeflow. And then you go to the model registry, and the trained model serves again in production, and again you have monitoring. But the difference is the CI/CD/CD. So in reality, MLOps pipeline in the real world look different. It's not perfectly level 0, or not even maybe level 1, but with lacking a bunch of components. So let me just go quickly through this. So this is one example. You have some experimental data and some raw images. and somebody, it could be even the data scientist, manually copies the raw images into another raw image repository, and then this is manually pre-processed. Then it generates machine learning ready images, and these, are manually triggered machine learning training. So you do the orchestrated experiment here, and then you have your trained model, you evaluate it and you validate it here, and then you have some monitoring here, and this is also manual. You have a person here looking at this, and then you're happy with what you see, and you deploy to a prediction CSV, which goes and consolidates into with more data that you have, for like in production. So you essentially have some data, and you append new predictions to the data that you have, which is already useful for our scientists. And then you have some data warehouse where this gets combined with the consolidated data pulled from the data warehouse plus the predictions, then go into our systems, into the Roche systems, where it's called the embedding side, where you're mapping your predictions to the systems that we have, and where the scientists can actually use them. And then maybe you get some new data, and then you start over. So this is actually more in reality, and it really highlights the complexity of MLOps in real world, not like some textbook. And so where to start? Like, you want to know where to fill the gap. So for example, there's this new risk, right? The European Union is coming up with new regulations in high areas to provide proof of its safety, including risk assessment, documentation, explaining how the technology is making decision. So you mitigate, aside from implementing a level 2 MLOps maturity level, invest in explainable AI. And then there's a bunch of technologies here and you can use for that. Other risk, serving endpoint being unavailable, and you're producing this, you have this like mission critical service, and then what happens if the endpoint is down? So you need to deploy systems with high availability, scalability, and performance, like Kubeflow and Kubernetes. What happens if you have incorrect predictions for a given sample? So you have to really then focus first on performance monitoring or single developer risk. What if this model is incredibly sophisticated, but there's only one person that knows this? So focus on reaching full automation with Google Maturity Level 2. So you decouple from a person, you have pipelines that run automatically. These are some of the references, and thank you very much. I appreciate any comments or questions, and have a wonderful day.